Okay, thank you very much for the introduction. So yes, I'm going to talk about some work that I started during my postdoc, and then over the years this has also been carried out most recently by our PhD student Shijun in applied maths in Sheffield, and this is also in collaboration with Ashley Willis and Professor Shusheng He also in Sheffield. So I'm going to talk about the transition to and from turbulence in a vertical heated pipe. So this is a very interesting configuration, which is also widely used in applications. So for example, cooling of nuclear reactors, or geothermal energy capture, or heat exchangers in fossil fuel or chemical plants. And so in the isothermal case, the volume flux is driven by an externally applied pressure gradient, and the flow is referred to as forced. In a vertical configuration, the buoyancy resulting from the lightening of the fluid close to the walls can partially or fully drive the flow, and this is referred to as mixed or natural convection. So what we're interested in here is to try and understand the different flow states and transition between flow states and how this affects heat transfer in the presence of buoyancy. And this is actually not so trivial, but a general picture has been drawn. So this is a figure that shows a measure of heat transfer, the Nusselt number, and here this buoyancy number is a measure of heating. So the downflow case, so in this case actually buoyancy acts opposes the flow, and in this case actually you get increase or enhancement of heat transfer. But what we're interested here is in the upflow case. So in this case, buoyancy can assist the flow, but you get deterioration of heat transfer. So we see here that, so this is a Nusselt number normalized by its, the value in the case of forced convection. So we see that as we increase heating, we have a strong drop here in the Nusselt number. So this is largely due to suppression of turbulence or laminarisation. And then as we further increase buoyancy, we start to drive convection-driven flow, and we start to recover heat transfer. So this is the general picture that has been drawn, but there are still several open questions that we want to try to address. And in particular, we want to focus on the dynamical characteristics of the flow and transition between different flow regimes, because we have this competition between shear-driven and convection-driven mechanisms that affect the flow, and then this also will affect the heat transfer. So in this talk, there are three main questions that I want to address. So in the first one, we want to try to understand how buoyancy suppresses the shear turbulence and then leads to heat transfer deterioration, which of course is bad for applications in cooling and heating application. And we want to connect this to some recent flow control strategies that are aimed at relaminarizing the flow. In that case, for transport applications, this is something desired to relaminarize the flow. Then the second question, we want to try and understand how this convective-driven state is triggered and it's sustained. This might be very different from the shear-driven turbulence. And then finally, we have these different flow states, and how can we maximize heat transfer in each of these different flow regimes. So this is for applications. Okay, but before talking about heated pipe, I have to go back to the isothermal pipe flow case. And of course, I need to mention Reynolds experiments. So as I'm sure you're all familiar with, Reynolds was already surprised, as he writes in his paper. He was expecting to find a linear instability of the laminar base flow, through which the flow gradually and increasingly becomes more chaotic and then leads to turbulence. But instead, what he was found was that transition was occurring in a quite sudden and abrupt way. So these are the typical characteristics of the so-called subcritical transition to turbulence that Tom, thank you, already talked a lot about. And this is not only happening in pipe flow, but also in other shear flows like blink wet flow. So in this case, the laminar state is linearly stable at any flow rate. At least all theoretical evidence point to this. Yet we observe or we see turbulence in applications or in reality. So the implication of this, or one of the things that needs to be taken into account, is that nonlinearity is important in this problem. So the transition must be initiated by finite amplitude disturbances. And Reynolds himself was already quite puzzled by the fact that depending on the level of ambient noise or disturbances in the lab setting, the flow rate or Reynolds number at which turbulence can be observed could be varied over a wide range in a very tightly controlled environment up to a very, very large Reynolds number. So when laminar pipe flow is disturbed at finite amplitude, it may transition to turbulence or not, depending not only on the Reynolds number, but also on the level and form of disturbances. And this is what makes this problem very hard to study theoretically, because we need to determine this threshold for transition to turbulence, which is a nonlinear instability threshold, depends both on the Reynolds number and on the disturbance, details of the disturbance. So this very highly nonlinear picture has been recently, fairly recently, rationalized through ideas taken from dynamical system theory, as again also was mentioned before. So here we visualize, or we analyze the flow as a huge, formally is infinite dimensional dynamical system. So here I rewrite this F here is the right-hand side of the Navier-Stokes equation, which depends on our control parameter, the Reynolds number. And we can visualize the solution in phase space, where the flow evolves along a trajectory which is organized around various invariant sets and their stable and unstable manifolds. So this dynamical system approach was sparked by the discovery in the early 2000s, in the case of pipe flow, of new finite amplitude invariant solutions of the Navier-Stokes equations, which are disconnected from the laminar state. And these solutions display simple dynamical behavior, like, for example, equilibria, which are steady state, or traveling waves, which are steady in a co-moving frame, or periodic orbits, which repeat itself after a certain period. And this figure here shows some of these traveling waves that were computed numerically, and also with different rotational symmetries. And also, most importantly, they were observed in experiments. So this confirms or shows that at least transiently they're present in pipe flow turbulence, and so they are dynamically relevant. And they also exhibit spatial coherence. So here the color coding corresponds to the streamwise, the downstream component of the streamwise velocity. Red and blue, it means higher or lower than the laminar pipe solution. So you see here this alternation of fast and slow lanes. And so these are the streaks that we also saw before. And the arrows represents the cross-flow components of the velocities, so this corresponds to the streamwise vortices or rolls. So these exact coherent structures, as they are referred to, because they are dynamically simple, spatially coherent, exact solution of the Navier-Stokes equation, they capture these streaks and vortices, which are the building blocks of turbulence. And so they organize the state space with their stable and unstable manifold. So how does the phase space of linearly stable flow look like? So we can visualize this, for example, in a 2D projection. So we have, and I will have a similar sketch to what was shown before, which is great. So we have the laminar point down here, which is a steady state, and it's stable to infinitesimal disturbances. And then up here, we have turbulence, which is much more messy, and for high enough Reynolds number, it's also an attractor. So we have coexistence of two attractors. So there is a basin, but there is a boundary that separates the two basins of attraction. So if I start here, I go back to laminar. If I start here, I go to turbulence. And some of these traveling waves or some of these invariant solutions that have been found are embedded in the edge, this laminar turbulent boundary, and they are believed to mediate the transition to turbulence. And a very important point in this two-dimensional projection, which was also mentioned before, is this point here where the edge comes closer to the laminar point. So this is called the minimal seed for transition. It is the disturbance of smallest amplitude that can just trigger turbulence. So if turbulence is something that we want to avoid, it is the most dangerous disturbance that can trigger turbulence. Yes, go ahead.
I'm allowed to interrupt, but have you left a gap in your green edge states deliberately?
No, there should be, yeah. Well, yeah, I mean, these are also interesting questions. There could be holes there where things can escape, yes, but this was actually by mistake. Very, very good observation, thanks, yes. Okay, so yes, this minimal seed. So how do we find this? So we can find this by solving a nonlinear optimization problem. I agree it's not easy and it's very computational expensive. So basically in a nutshell, what we do is we, over all possible disturbances of some initial energy E node, so lying on this ball around the laminar point, we want to find the disturbance that maximize the energy growth after sufficiently long time t opt. And we solve this using a direct adjoint looping, which is based on the full Navier-Stokes equation. It involves forward and backward integration of Navier-Stokes and backward of the adjoint equation. So yes, it is computationally expensive. And then we gradually increase the initial energy E node until we finally trigger turbulence. So the minimal seed will be bracketed between these two final initial states. And if we look at the time evolution of, for example, energy starting from the minimal seed or just above it, we see that we can trigger turbulence, but even disturbances that decay, they are transiently amplified. So this is this transient growth mechanism that, again, Tom talked a lot before, much more in detail than what I will say here, so that's great. You know everything already. So this transient growth mechanism, which is rooted in the non-normality of the linearized operator of the Navier-Stokes equation, and basically what we find is that the linear no-modal disturbances, so the one that maximize transient growth, in the case of laminar pipe flow, are streamwise vortices. So this is the linear no-modal optimal. And these streamwise vortices lift up the slow-moving fluid close to the wall towards the center of the pipe, and at the same time push down the fast fluid in the core towards the wall. And in this process, they create these streamwise velocity defects or streaks that you see here, the slow and fast streak here. And key to the efficiency of this mechanism is that the small amplitude streamwise vortices can generate large amplitude streaks. So this is still a linear picture, and we know that this is not enough. We need nonlinearity. So this nonlinear optimal disturbance that we find with this nonlinear optimization problem that I mentioned before. So in this case, it is localized both in the wall normal and azimuthal direction, and initially comprises both streaks and vortices. And then it very rapidly unpacks to OR mechanism, and then also take advantage of the lift-up mechanism as well. But in this case, these different linear mechanisms are coupled non-linearly to give rise to largest growth. So this nonlinear optimization problem, coupled with a search over the initial energy, gives us the minimal disturbance that can just trigger turbulence, and it also gives us a measure of the nonlinear stability of the laminar state in the form of this critical amplitude of the minimal seed. So all of this is the picture of the transition to turbulence. So what about the transition from turbulence? So the relaminarisation problem. So again, we're talking about isothermal pipe flow, but we've seen that in the case of heated pipe, the relaminarisation or suppression of turbulence is something undesired. In the isothermal pipe flow case instead, for example, for application of transport of liquids or gases, suppressing turbulence might be highly desirable because it leads to energy savings and reduced carbon emission and so on. So some experiments that were performed recently by some of my colleagues at the Institute of Science and Technology in Austria, where I spent 2 years of fellowship. So they perform some experiments where they show that, quite surprisingly, by momentarily increasing the turbulence or momentarily increasing the shear, they were able to obtain a full collapse of turbulence. And they did this through various large-scale manipulation of the flow. So for example, in this case here, they were just putting these rotors in the pipe that vigorously stir the flow. So initially, turbulence is increased, but then farther downstream it decays. Or another method consisted in putting a stationary obstacle. It basically would be here or here, a stationary obstacle in the center of the pipe that partially blocks the flow. So again, immediately downstream, you increase the turbulence, but then you see that it further laminarizes. And we were also able to capture this phenomenon in simulations. So they also had other methods, but basically the common feature of all these methods to relaminarize the flow was this flattened mean streamwise velocity profile, like you see here. So in this case, the turbulence was destabilized by this flattened profile, which basically interrupts the continuous energy transfer from the mean shear to the heading motion, and then leads to the collapse of turbulence farther downstream. So to understand how the mechanism of relaminarization behind these experiments, they mostly look at the self-sustaining process of turbulence. So again, this picture of the turbulence regeneration cycle that was explained before, and which basically boils down to 3 parts. So this leg here results from the transient growth mechanism that I mentioned before. So the streamwise vortices advecting the mean shear and creating streaks. And then their streaks undergo some instability and then recreate the vortices by nonlinear interaction. So in all of the cases in the experiments with different control methods, they found that transient growth was reduced compared to the uncontrolled case. So basically they attributed the relaminarization to the suppression of the lift-up mechanism in the presence of this flattened profile. And this was measured by this reduced transient growth, which basically disrupt the turbulent cycle behind recovery. So it is this leg of the self-sustaining process that was affected and interrupted. And so then this regeneration cycles breaks down. And we also looked at the effect of flattening the profile to the minimal seed for transition. So remember, this is the smallest disturbance that can just trigger turbulence. So we basically conducted that nonlinear optimization problem. We solved it with this flattened laminar profile, where this delta is the difference from the Eigenpoisel parabolic solution. And what we found is basically a complement effect to what was shown in the experiments. So we showed that flattening enhances the nonlinear stability of the laminar state. So this minimal seed is pushed out, meaning that you need larger amplitude disturbances in the first place in order to trigger turbulence. Okay, so what does all of this have to do to the heated pipe flow case? Well, we've seen that with increasing of buoyancy or heating, you can have suppression of turbulence, and also in these cases, we will see that we can find this flattened profile. So first I will just talk a little bit about the model that we use for this vertical heated pipe. So we consider upward flow through a vertical heated pipe, which is subject to a background axial temperature gradient. So we assume that temperature, the boundary temperature increases linearly in the streamwise direction. This is a model that is often used by other authors, but differently by other models. We consider a temperature-dependent time-dependent temperature gradient. So this A here depends on time. And this is because we want to be able to model how the heat transfer is affected by the different flow states and the nature of the flow. So basically, this time-dependent temperature gradient can change in time depending on the way the fluid flows. So this reflects the flow-dependent nature of the heat transfer in this case, which we want to capture. So the temperature fluctuations satisfy the advection diffusion equation, which in non-dimensional terms we write in this way, and this term here, so this is basically a sink term which withdraws energy or heat that enters via the pipe boundary. And this A is also adjusted to maintain a constant bulk temperature. So heat enters via the pipe walls, and it's withdrawn by this sink term to keep the bulk temperature constant. So we also use Boussinesq approximation, so we can write the Navier-Stokes equation with additional buoyancy term. So this term here, again, after non-dimensionalization, which is, so this buoyancy force which is proportional to temperature fluctuation. And this parameter here, C, so this is basically measures the ratio of buoyancy force with respect to the force that drives the laminar isothermal pipe. So basically the laminar isothermal pressure gradient. So this C here is a measure of the intensity of heating. So it will be an important parameter for us. So to perform the simulation, we have extended the open pipe flow solver of Ashley Willis to include this effect of heating. And the results, the DNS results that I will show you, they are all for a length of a pipe of 10 radii and for a fixed Prandtl number of 0.7, which is typical of gases. So first, if we look at the laminar profiles, we see that as we increase C, so this buoyancy parameter, we see that the laminar profile becomes flattened, and then as we increase it further, we start to have this M-shape profile, which, as we will see later, can undergo a linear instability. And we also validated our model with experiments. So this is just to show that we can get good agreement with experiments. This is, again, the similar plot that I showed at the beginning with Nusselt number normalized by the isothermal value versus here is a buoyancy number that is defined in a bit different way. But basically what I want to show here is we can capture or get good agreement with experiments. So if we look at the fact of increasing this buoyancy parameter C that measures the effect of heating, so we can perform simulation at a fixed Reynolds number, and we see what happens to the heat transfer as we increase C, and to the flow states as we increase C. So this Nusselt number is our quantity of interest because it is a measure of the heat transfer effectiveness. So if we start from low C, for example, C equal to 1, so in this case, pretty much we have shear turbulence. It's the same as in the unheated case. And then as we start increase C, then we have full laminarization, and then correspondingly we have that heat transfer is strongly deteriorated, so it drops a lot. And as we increase further, we start to drive this convection-driven state, which is quite quiescent at low C, and so this Nusselt number is not much larger than in the laminar case. So this convective turbulence has a much lower turbulence intensity, so much lower energy, and also a much smaller Nusselt number. And to understand how heat transfer is deteriorating in this case, in this convective driven state, we can compare, we can look at how the flow in this cross section. So these are contours of the total streamwise velocity. This is for a shear turbulence case, and this is for the convective turbulence case. So we see that in this higher C case, we basically, the flow close to the wall is almost steady. So we lack those near wall vortices which lift up the fluid and then mix things between close to the wall and in the center. So we lack these near wall vortices or rolls that enhance the mixing. And then this is why we get this much lower heat transfer in this case. So we have performed a bunch of simulations for different Reynolds number and different values of this buoyancy parameter C. And this plot basically shows the flow map that we get from these simulations. So the blue symbols represent a region of shear-driven turbulence. Green is for laminar, and red is for this convection-driven flow. So at low Reynolds number, the progression is like I mentioned before. So initially we go from shear, from the shear-driven turbulence, we fully laminarize, and then as we further increase C, we start to drive this convection-driven state, which enters via a linear instability, as we will also see later. But this green region then at higher Reynolds number becomes narrower, and then at higher Reynolds number we switch directly from the shear-driven turbulence to the convection-driven flow. So first we want to understand how the shear turbulence is suppressed. So this was the first question that we want to address. And to do this, we can look at flow visualization, for example, at Reynolds 5300. So here we have isosurfaces of streamwise velocity, which are representative of the streaks, and here of streamwise vorticity, which is representative of the rolls. And we compare the isothermal case with the heated case. So we see that in the presence of heating, the streaks are not very much affected, while the rolls are much reduced. So this suggests that it is the suppression of the rolls rather than the streaks that leads to the laminarization. And we can compute traveling wave solution. So for example, we can continue known traveling wave solution from the isothermal case to the case where C is greater than 0. And if we do that, for example, from these solutions that are embedded in the edge, we find that also they are suppressed. So this is in line with the fact that the edge is pushed out from the laminar state. But what's more interesting is to look at the dynamics starting from this traveling wave solution. So the red one, so here I'm showing, yes, starting from this traveling wave solution edge state. In the isothermal case, this solution lies on the edge. So if I shoot in opposite direction, one goes to turbulence and one goes to laminar. But in the case of C equal 4, for example, we see that instead, in both cases, even if I shoot up towards turbulence, turbulence is not sustained. So this one decays. But we see that there is still a large initial amplification. So there is still transient growth. And it's quite similar to the unheated case. So even if turbulence is not sustained, we still have this large initial amplification. And if we look at the mean profiles, we see that while shear turbulence is still present, so for this cases here, so this blue line is basically like a shear turbulence, and up to C equal 5 or even 7.5, we see that the profiles are almost identical. So it makes sense that transient growth is not affected, and indeed we see that laminarization happened despite little suppression of the streaks. So the overall picture that we draw from here is that while the streaks are important for the non-linear saturation of the flow, it is quite easy to drive these streaks. So weaker vortices can still create streaks of the same amplitude, and then criticality for relaminarization happens when these vortices are too weak, and then the flow, the turbulence is suppressed. So basically close to criticality, the rolls are more important for this relaminarization process. And this is quite different from the picture that was proposed in the experiments in Vienna and also in the previous work. So in those cases, instead, we saw that the mean profile was modified by the different control methods that they used. So in that case, it makes sense that it is the transient growth that it is affected, so this leg here. However, this is still very much open question, so I will not go into this, but some of our recent work suggests that even in that case, actually, the relaminarization can be more closely related to the suppression of the vortices due to a suppression of this streak instability. So I will actually have a position advertised, a postdoc position advertised on looking at this part of the work, which I will also show at the end of the talk, but this is something that I will want to look at in the next few years. So the other question was the transition to convective turbulence. So here we see that at low Reynolds number, convective turbulence appears around C equal 4, and this has also been related to linear instability that enters at this value of C. And then this critical value of C for the switch to convective turbulence then moves to larger values as we increase Reynolds number. So there is a competition between shear-driven and convection-driven mechanisms. So we want to understand a little bit more how this convective-driven state is triggered and sustained. So first we revisited the linear instability. So we found that the most unstable mode is always of azimuthal wave number n equal 1, and it can have streamwise wave number k equal 1 or 2. So the corresponding eigenfunction will look like something like this, where the disturbance is concentrated or active in the center or core of the pipe, consistent also with what we observed in the simulations. And we see that the linear instability appears at around C equal 4, consistent with our simulations. So it confirms that this convective turbulence enters via a linear instability. But interesting, we see that these eigenvalues or growth rate plots, they show quite complex behavior. And the flow is not always linearly unstable for C greater than 4. So it appears first at this C equal 4, but it's not always linearly unstable for C greater than 4. So we have a region of restabilization around C equal 5 or 6, depending also on the Reynolds number. So we want to exploit this to perform nonlinear, non-modal stability analysis in the case of heated pipe. So we've seen that for the isothermal case, when the laminar state is linearly stable, we need to resort to nonlinear, non-modal stability analysis in order to examine the transition. And in this case, at Reynolds 3000, this is the case that we focus on, flows, nonlinear flows with values of C between 4 and 6, they show, they exhibit the flow states in the convective turbulence regime, but in the case of C equals 6, it is linearly stable. So convective turbulence is sustained, but it is linearly stable. So we perform, or we solve that nonlinear optimization problem. In the case of heated pipe, we extended our method to take into account the effects of heating, and we want to study how the minimal seed changes as we increase C, this buoyancy parameter. So first, we focus the results on the case of C smaller than 5, because this case of C equals 6 is a bit different. So here, this figures are just comparing the isothermal minimal seed case, which I showed before, with the heated case. And we see that it's essentially similar, but these structures move closer to the wall, so they become thinner, basically, and closer to the wall. And this is due to this flattened profile. So we observed this also for cases with C equal higher than that, up to 4. And then for the case of C equal 5, we also have a branch, we found another branch which is basically approaches the linear unstable eigenfunction. So they have these two different branches. But what's also interesting is that as we increase the buoyancy parameter C, the initial energy needed to trigger turbulence also increases, and the growth that we obtain is much reduced. So this suggests that methods that are used to trigger shear turbulence in isothermal case might not be so efficient in this case if you want to enhance the heat transfer. So looking at the case, an interesting case of C equals C, so in this case, we were not able to find those structures similar to what I showed you before for the lower C case. So this, the branch of nonlinear optimal that triggers shear turbulence in isothermal case could not be tracked beyond C equal 5. But in this case, we found something different. So starting from a very small initial energy and extending a lot the time horizon, we found a new nonlinear optimal disturbances. So this looks very different. So it is mainly active in the center of the pipe, and it has these two pairs of streamwise vortices. And actually, the cross-flow components here are much smaller than the streamwise one. And if we look at the transition process starting from this minimal seed to convective turbulence, we see that it triggered convective turbulence directly, but over a very long time. So we see that, so these two cases here, and ignore also the timestamps here, these two cases here would be the bracketing one, and we see that they are very close up to a long time horizon. That's why we need a very long optimization time. And then this one leads to turbulence, and then the other one decays. So basically this, we see that here we can track the edge for quite a long time, even with small refinement of the initial energy. And we also found some edge state here, which are less, or they're less unstable than in the isothermal case. And going back now to the case of C equal 4, so we look at the transition process in this case and comparing transition process starting from the minimal seed and different unstable eigenfunction. So if we start, so this plot shows perturbation kinetic energy, time evolution, and if we kick or if we disturb with the flow with the minimal seed, we see that shear turbulence can be triggered. We can recognize because of these higher values of perturbation kinetic energy, but it's not sustained, so it then quickly drops and to the convective turbulence value. And if we use the different unstable eigenfunction to perturb the flow, we see that we are approaching either a traveling wave solution or a periodic solution. So we put this into a Newton root finding algorithm, and we were able to converge them to an exact coherent structure. And we can look then at how the structures change along the period of one of these periodic solutions. So this video, which I will now play, show the streamwise velocity and for one of these periodic solutions that we were able to converge. So we start with a perturbation that looks similar to the unstable mode that we trigger to, and then we see that this perturbation grows, and the fast-moving fluid in the center, this region start to merge, forming these streaks that then breaks down, and when the streaks decay, then the roll perturbation reappear. So basically, this periodic solution distill these three typical processes that sustain the convective turbulence: the growth of the unstable mode, which then forms this sinuous streak in the middle in the middle, and then these sinuous streaks break and decay, and when it decays, then the unstable mode forms again, reappears again. So we observed these typical processes also in, so this was for the periodic solution, but we observed this also in the transient convective states for C4 and even up to 10, but in those cases the flow is much more chaotic, so it's more difficult to distinguish these three processes clearly, but we do observe this in the nonlinear flows as well. So we see that convective turbulence is sustained by these three typical processes, which are related to or they're driven by the appearance or suppression of linear instability of the mean profile. So this is very different from that self-sustaining process of shear turbulence, which instead occurs without any linear instability of the base flow. Okay, so how much have I got left?
20 minutes.
Oh, okay. Okay, so then in the last part of my talk, I want to talk a little bit about heat transfer optimization. So we've seen that we have, as we increase buoyancy, we see that we have these different flow states, shear turbulence, laminar, and convective-driven state, and correspondingly, the heat transfer can change a lot. So when the flow laminarizes, we have this strong heat transfer deterioration, which of course is bad for application. So the question that we want to address now is how can we maximize heat transfer in all of these different flow regimes? And this can be solved using variational methods. So basically, we can extend our nonlinear optimization problem that we've seen before to calculate minimal seed, the minimal perturbation to trigger turbulence in both isothermal and heated cases. So we can use a similar method here to maximize heat transfer. And this has also been done by previous authors, but in those cases, they looked at the steady velocity field that can maximize heat transfer. So they've assumed a laminar steady flow. So basically, in this case, they're not able to take into account the dynamical characteristics of the flow, or we've also seen that the flow can be turbulence and transition to different flow states. So we want to be able to capture all of this. So instead, what we do here is to maximize heat transfer by optimizing a time-independent body force that can modify the time-dependent flow. So we want to take into account how the dynamical characteristics of the flow can affect the heat transfer. So we can use the Lagrangian multiplier framework or variational framework, similar to what we've done before. So we introduce a body forcing to the Navier-Stokes equation, and we use this adjoint framework to find the optimal spatial distribution of this force that can maximize heat transfer. And we suppose that we are limited, or the magnitude of this force is limited, and it's some value A naught. So we can write down our Lagrangian, and so the objective function here, this J, that we want to maximize. So here we use what's also been used in other applications with heat transfer. This is referred to as scalar or thermal dissipation, or in the thermal engineering community, this is also been known as entrancy dissipation. But basically, yeah, this is a measure of the ability or the heat transfer ability. So this is what we want to maximize, subject to various constraints. So this is to constrain the amplitude of our forcing, and then this is subject to the full time-dependent Navier-Stokes temperature equation, and so on. And we solve this optimization problem at Reynolds 3000 in each of these different flow regimes, so for different values of C. So what we're interested in, as I mentioned before, is how time dependence of the flow affects the optimization in each of these different flow regimes. So starting with the laminarized regimes, so at C equal 3. So this figure here shows Nusselt number, so this measure of heat transfer, normalized by the unforced value. This is for optimized forcing with different amplitude A naught for each curve. So we can see that with this optimized body forcing, we can greatly improve the heat transfer. So for example, in this case, it's 50% more, and it can become even double. And if we have strong enough amplitude of this forcing, it can also trigger turbulence. And you see with the orange line towards the end of our optimization time horizon, we see that it triggers turbulence and the Nusselt number increases a lot. So what does the structure of this optimal body force look like? So here, these are arrow plots. I'm not showing the stream, which show the cross-flow components of this optimal body force. I'm not showing the streamwise component because we always find it to be much smaller. So, and this shows this amplitude-dependent shape of the optimal body force. So we see that this body force is such to induce axially independent rolls, which have a different rotational symmetry. So we see that the number of optimal rolls increases with the amplitude of the forcing. And this is quite consistent with what was found before with the steady state calculation. So we found that this optimal forcing is in the form that induce this actually independent rolls or longitudinal swirl flows with multi-vortex structure of different azimuthal wave number. And what's interesting here, which you might have noticed, is that in this case, this green line here, much later on, we also trigger turbulence, but in that case, the transition doesn't lead to a larger Nusselt number, so indeed actually decreases. And this is quite surprising because instead the roll energy increases in this case as well. So the energy of the rolls is normally associated with the enhancement of mixing and so better heat transfer. So in this case it still increases a little bit, but it's not leading to an improvement of heat transfer. So that's interesting, and we want to try and understand this a little bit more. And to do this, we look at some visualizations of the radial temperature gradient at the boundary. So this is for the case of forcing, which has an azimuthal symmetry or fourfold rotational symmetry, this OF4. And this is the top one is for lower amplitude of the forcing, and this is for a larger one. And on this side, you see the forced laminar state, and here the forced turbulent state. So you see that on the top line, so going from the forced laminar state to the forced turbulent state, this region of high heat flux, so the yellow one, intensify a little and also widen. And so indeed, in that case, we had enhanced heat transfer with the transition into turbulence. And in this case here at the bottom instead, we see that these regions of high heat flux, they also widen, but they become less organized and actually become weaker, despite the energy of the rolls being increased in this case as well. So we see that in this case here, transitioning to turbulence, we see that the rolls are not as efficient to increase heat transfer. And this is due to the unsteadiness of the rolls in this forced turbulent state. So these rolls are intermittently placed farther from the wall, so they're not consistently placed close to the wall where they're most efficient at increasing heat transfer. And then consequently, we have this reduction of heat transfer. So triggering turbulence does not necessarily improve heat transfer. It also depends on the position of the rolls, and so the unsteadiness of the rolls is an important factor here. And then looking at the shear turbulence case, now the optimization in the shear turbulence case, so C equal 1. So here it is a little bit more tricky because the flow is chaotic, so we cannot have a long optimization time horizon. But we see that with the short time optimization, we can still improve heat transfer relative to the unforced value. And here this N is number of initial conditions that we use because the flow is turbulent, so we need to make sure that our method is robust to different initial conditions. So in this case, for shear turbulence, it's now obvious that we can improve heat transfer because we know shear turbulence is already quite good at that. But we see that we can get, even in this case, with a short time optimization, we can still get a heat transfer enhancement. And it is interesting then to compare in this case, okay, yeah, here, just wanted to show that also in this case, the optimal shape of the forcing is also in a form that induces rolls. And what's interesting is to compare what we get with this short time but turbulent optimization in the case where we instead assume the steady two-dimensional flow, so similar to what was done in previous calculations. So this form of the rolls, we still get it like in previous calculation, but now we have a fully time-dependent flow we're optimizing with, so we want to see the effect of this compared to the steady flow assumption. So this is just showing the enhancement of Nusselt number, and solid is for our short time unsteady optimization, and dashed is for the steady one. So we see that particularly for higher amplitude of the forcing, A naught, we can get a larger heat transfer enhancement compared to optimization done with the steady flow assumptions. And to understand why is that, we see that if we compare the structures, we still have rolls, but in our case, with the unsteady, the optimization done with unsteady turbulent flow, we get that these rolls are closer to the wall, and so they are able to enhance heat transfer more. In the convective turbulence regimes, okay, the results here are not so interesting. Well, basically what we get is that for weakly convective turbulence, the forcing can either laminarize the flow or have a weakly chaotic flow, and in these cases we're still able to enhance the heat transfer. And for larger C, so when we start to drive this more chaotic convective turbulence, we see that the results are similar to the turbulent shear turbulence case. So we have that the optimization done with the unsteady turbulent flow leads to higher Nusselt number enhancement, and this is due to these rolls being placed closer to the wall. So basically the key takeaways from this last part is that doing optimization with chaotic or time-dependent flow does not destroy the fact that inducing rolls is optimal in enhancing heat transfer, but it does affect the number of rolls and the radial position. So this is something that might be useful to take into account when designing things, like for example some ribs structure that can induce these rolls when designing these things to enhance heat transfer. And also we've seen that triggering turbulence does not lead necessarily to the expected results of improving heat transfer. Okay, so maybe I just leave the conclusion slide here. But before doing that, I just wanted to, I was told that I can advertise position, so that's what I'm doing here. So yes, I think maybe tomorrow or next week, it will appear on jobs.ac.uk. I have a 3 years postdoc position looking at relaminarisation in isothermal pipe flow, so looking at how those structures are affected and trying to understand that a little bit more. And I will also have a PhD position, this may be starting later on. But anyway, if you're interested or know anyone that is interested, please contact me or just talk to me at the lunch break. Okay, so I will just leave up my slides with the conclusion here, and